everyone. In today's video, I will be explaining how you can determine the relative acidity of a group of organic compounds relative to each other. So, before we get into organic compounds, let's take a look at some of the more common acids that you may have heard of, and we will use those common acids to understand the relative acidity of other compounds. So to look at these acids, I'm just going to use all of the halogen protonated acids. So we will use HF, and we will use HCl, we will use HBr, and we'll use HI. So again, these are just the four acids that we get from the four halogens. And if we take a look at the periodic table, so I'll do it in red over here, we know we have our halogens off to the far right end of the periodic table, and we get fluorine, chlorine, bromine, and iodine. That will come in handy later. So when we talk about the strength of an acid or what makes an acid more acidic, we look at the pKa. Now, what is pKa? pKa is essentially a measure of how willingness a compound is to release its proton, or its hydrogen, in other words. So again, I'll just give a general definition. pKa is a measure of ability to deprotonate. So the lower a pKa, the more likely it is to exist in the deprotonated form, the more easily it is deprotonated. So if we look at our four common acids using the halogens, we have HF starting at the top of the group going down to HI. And if we write out their pKa's, HF has a pKa of around 3. HCl has a pKa of around -6. HBr has a pKa of around -9. And then HI has a pKa of around -10. Okay, so as we can see, going left to right with these acids, so from fluorine down to iodine, we see a decrease in pKa, which leads to a more acidic compound. Because again, when we say something is more acidic, we say it is more willing to give up the proton that it has bound to it. So this is where we're going to take this knowledge and we're going to apply it to some organic compounds. So if we compare our pKa's to our group over here, we'll write it out this way. We'll say -3, we'll say -6, -9, and -10. As we can see, going down the group, we're getting more acidic. What this has to do is this has to do with the size of our atom. So fluorine, we know, is small, and then chlorine gets a little bigger, bromine gets a little bigger, and then iodine is huge in the group. So when we're looking at the atom that the proton is attached to, one thing we want to look at is we want to look at the relative size of that atom. And then in addition, we want to look at the relative electronegativity. However, in the group, all the halogens, although fluorine we know is the most electronegative, all of the halogens are extremely electronegative. So here we divert to looking at the atomic size, and we can say the larger the atom, the lower the pKa is, the more acidic that compound is going to be. Okay, now if we take this knowledge and we apply it to some organic compounds, let's take these 4 compounds. We'll do all ring structures. We'll do this compound. We'll do this compound. We will do the protonated form of this compound, giving oxygen a plus charge. And then we'll do sulfur compound, again, plus charge. And then we'll do a selenium compound. Okay, now we've moved over to organic compounds. We have carbons involved. We're no longer looking at inorganic acids. So looking at this group of compounds, again, we go back to the periodic table. So oxygen is one group to the left of the halogens. So we call it to be group 6. Halogens are group 7. And so looking at the periodic table, we have oxygen here, and then right below oxygen, we have sulfur, and then below that, we have selenium. So if we look at that group, of compounds, we can see that oxygen going down to sulfur, going down to selenium. Again, remember the periodic trends. As we go down a group, we get larger in atomic radius, so our atoms are getting larger. So we're going to apply that same principle of atomic radius increasing to these compounds. Now you've noticed I have one form of the oxygen that is already deprotonated. It's in our neutral form. And then we have the protonated oxygen, which is in our positive form, or our positive cation of the oxygen. And so when we look between those two, we know that those two compounds are going to be the least acidic of the two groups because oxygen is the smallest of the atoms that we have here protonated. However, the oxygen that does not contain a proton, that does not have a bonded proton already, is going to by far be the least acidic because it doesn't have a proton on that heteroatom to give up. Whereas our positively charged oxygen does have that one proton that it can very easily give up to get our neutral oxygen. So when we rank these in order of acidity, we're going to call our neutral oxygen, we're going to say that is least, or that's less acidic than our protonated oxygen. And then our sulfur, because it's larger than the oxygen, but smaller than the selenium, that's going to be our next one. So the sulfur is going to be the next most acidic in this group. And then our positively charged selenium is going to be the most acidic compound in this group. Again, that has to do with the atomic size. The larger the atom, the more stable it will be when it releases its proton, especially since we're going down to the neutral form. So as I drew them initially, we will have an increasing relative acidity. And we could put the pKa values for these compounds, but for the purposes of this video, we're just trying to figure out within a group which compounds are more acidic relative to the rest of the group. And so we'll call this one most acidic, and we'll call this one over here least acidic. Okay, now moving away from looking at compounds with trends based on the atomic size of the atom that the proton is connected to, we're going to look at another determination of acidity based on something called inductive effects. Now, inductive effects is essentially the ability of the molecule to distribute its electron density across the rest of the molecule because of another electronegative atom present. So for this, we're going to look at 4 compounds. And these compounds are going to be the exact same except for the position of this chlorine. So chlorine, as we know, a halogen, very electronegative. So if we change the position of this halogen, so we'll put one here, and then we'll come down here. And one more. So as we can see, between the 4 molecules I have drawn, our chlorine is just getting closer and closer to that alcohol group at the end of our carbon tail. And the closer this chlorine is to that oxygen group, the more stable the oxygen is going to be in its negative form. Now we know that oxygen is fairly electronegative and it's already happy in its negative form. It's already stable when it has a negative charge. However, having that chlorine there able to pull the electron density away from the oxygen, that allows the proton to leave even easier than it already would. So as the chlorine gets closer to the alcohol, we can see this somewhat of a localization distribution. So again, here versus here versus there. And we can see that our chlorine, the farther away from the oxygen, the farther that it would have to pull electrons if it were able to. So the closer the chlorine is to our oxygen, the more acidic the proton is going to be. And when we're talking about the acidity, we're always talking about the proton. The proton and how easy that proton can leave the molecule. So if we were to label these as 1, 2, 3, and 4, and we were to order them, we're going to order them with the most acidic being the compound where that electronegative atom is the closest to the proton that is leaving, and the least acidic is going to be where the electronegative atom, our chlorine, is farthest away from the proton that's leaving. So if we were to order them in the correct order for acidity, we'll say 1 is less acidic than 2, which is less acidic than 3, and finally less acidic than 4. And for some notes on this, again, increasing acidity due to inductive effects. And again, the inductive effects, you can just think about that as the ability of that localized electron cloud around the oxygen to be pulled away by that electronegative atom being in the area of the proton that's leaving. Okay, now that we have looked at the inductive effects, now let's look at we'll go back slightly to the atomic size, but then we're also going to look at the electronegativity of the atom. So again, I will draw 4 compounds. We'll draw one with a carbon, a methyl group coming off the top. We will draw one with an alcohol, one with a thiol, and then one with an amine. So again, methyl group, alcohol group, a thiol group, and an amine. So if we look at these compounds, let's again draw a portion of our periodic table. So again, we know we have fluorine, we have chlorine, we have bromine, and we have iodine for the halogens. Now let's work left across the periodic table. We know directly left of the fluorine, we have oxygen. And then to the left of the oxygen, we have nitrogen. And to the left of the nitrogen, we have carbon. Okay. And now we have our thiol group, so let's go ahead and draw in where our sulfur would be. So our sulfur is going to be in the same group as oxygen, just right below it. Okay, so for determining the acidity of these compounds, the first thing we want to do is we want to look at the electronegativity. So if we were to order these in order of electronegativity, we would put that our methyl group has a carbon. Carbon is going to be the least electronegative, so we will put carbon in last based on electronegativity. And then next up we have nitrogen. So this is going to be in the middle based on electronegativity. And then our oxygen and our sulfur were in the same group. So our relative electronegativities, although up and down the group they do change, our relative electronegativities here are fairly close. Therefore, for these two, we're going to divert back to our size comparison. So, using our size comparison, we can say that SH is more acidic than our OH, similar to that second example that we saw, because sulfur is bigger than oxygen. And we'll put because. Okay, so now that we can kind of see our order of electronegativities, if we look on the periodic table and we order these compounds in their relative acidities, we'll see starting at the carbon and then going down the group with sulfur, and we'll call this our increasing acidity for these compounds, these relative compounds. So if we were to reorder these in the order from least acidic to most acidic, we would of course have our methyl compound, and then we would have our amine, then we would have our OH, and then we would have our sulfur compound. Now, if we wanted to go in and write out these pKa's, the pKa of our groups here, so we'll put pKa's. For our methyl group, the pKa of a methyl group is around 50. And the pKa of amines are around 35. The pKa's of an alcohol, they're around 16 to 19, somewhere in that range. And then the pKa's of sulfur-containing compounds, or in this case, a thiol, they're going to be around the 9 to 10 range. So again, we see here that with our trend following the periodic table, going from our methyl group up to our thiol, we will see increasing acidity. So again, this is combining electronegativity trends with atomic radius trends. And if you can just apply this knowledge to any compound containing these four groups, you will be able to determine the relative acidity. Okay, and now I'm going to give one last example on how to determine relative acidity, and that should cover the spectrum of what you might be asked in terms of ranking compounds in order from least acidic to most acidic. So for this last example, I'm going to stick with my cyclopentane because cyclopentane is the best. So cyclopentane, we're going to look at a variety of oxygen-containing compounds. So first we'll look at a ketone. Next we'll look at an alcohol. We'll look at a carboxylic acid. And then we'll look at one that we've seen before, our protonated oxygen species. Okay, so for ranking these compounds in increasing acidity, first we need to look at what is going to make the compound the most stable. So going back to the first example we had with organic compounds, we saw the oxygen species that was protonated that had a positive charge. This protonated species wants to be deprotonated very badly because that oxygen, being such an electronegative atom, that oxygen wants to have a negative charge. So to make that oxygen negative, we got to get rid of that proton. That proton is easily released to make the oxygen neutral. And in fact, the pKa of this compound to get rid of that proton is around -2. So we can see we have a very, very low pKa. So that's a very acidic compound. That proton does not want to be attached to that oxygen. Okay, if we look back to our alcohols from the last example, we'll remember that alcohols have a pKa of, again, around 16 to 19. 16 to 19, so they can be acidic, but they're not the most acidic species that we have. If you look at our carboxylic acids, we have our carboxylic acid here. We get a pKa of right around 5. So with a lower pKa, we know that our carboxylic acid is more acidic. That makes sense, right? The name is carboxylic acid. We would expect it to be at least slightly acidic. And then looking at our ketone, the pKa in question, or the proton in question, are any one of these protons coming off of this end methyl group. With that ketone present, that will allow for a proton to leave that methyl group, but methyl groups usually do not want to lose their protons because that carbon is happy, that carbon is neutral. It does not want to acquire a negative charge. And for the pKa of, we'll say, this proton, the pKa for that is around 19 to 20. So again, the pKa of the methyl group is pretty close to the alcohol. The alcohol is only slightly lower because the oxygen is more electronegative than the carbon. So I'm talking about oxygen versus carbon. Oxygen is more electronegative than carbon, so it can more easily hold on to that negative charge. And just to see what this would look like if we were to draw our deprotonated forms, we would have CH2 with a negative charge. We would have oxygen with a negative charge. Same thing here. We get oxygen with a negative charge, but we still have this carbonyl. We'll talk about why that's important in just a second. And then here, now we just have our neutral oxygen. So these are all of the deprotonated forms, or we could call them the conjugate bases. Conjugate bases. Remember, those are just the deprotonated forms of the acid. And so why does this compound have a lower pKa than this compound? Well, this comes back to that magical word in organic chemistry, resonance. So we can draw a resonance structure for this compound where we have, I'll draw this in red. We've taken a lone pair, formed a bond here, and pushed a lone pair up. And so now we get the negative charge on this other oxygen. So if we were to draw the charge stabilized form of this, so again, resonance here, we could draw it like this. O, and then we have this negative charge distribution going around that dotted line. So that's what allows that compound to be more acidic. It's stabilized by resonance, and we can see that proton is more easily released because of the resonance stabilization. And then so lastly, to rank these compounds in order of acidity, and if we call this 1, we'll call this 2, 3, and 4. We will see them in exactly that order. So 1 is less acidic than 2, less acidic than 3, less acidic than 4. So increasing acidity. And that's observed by the pKa's. You will often have a chart of pKa's, so you can just find the pKa. The lower the pKa, the more acidic the compound is. So I hope this helps in understanding the relative acid capabilities of different organic compounds. And for a later video, we'll be talking about the mechanisms involved in acid-base chemistry with organic compounds.